So we're going to go now and derive the complex version of the Fourier series. Now I've written the Fourier series out here, and we've derived that in the previous videos. Now the idea is that we're going to take this equation here and just create one equation from it, and we're going to take these three here and create just the one simple equation for these three. And we're going to use these two identities in order to provide the complex version of the Fourier series. So we've seen here that cos n omega t can be written as e to the I n omega t plus e to the minus I n omega t upon 2. And we've seen that in the graphical calculator in a couple of videos previously. And that's represented as a phasor here in blue rotating in the anti-clockwise direction, that's e to the I n omega t, and a phasor rotating in the clockwise direction, that's e to the minus I n omega t. And it's going to map out this line here in pink, which will be the cos omega t, but it's going to be twice because it's the vector addition of these two, so we have to half it in order to get the cos n omega t. And equally we do the same thing with the sine, and the difference here is the sine's phasor here, which would have been rotating, that is rotating in the clockwise direction, actually starts off 180 degrees and out of phase because of the minus sign here. So these two phasors rotate and they'll give us this twice the sine. If we half it, it's divided by 2i, then we'll get the sine component. So we're going to be putting these in for the cos n omega naught t and the sine n omega naught t in each of these here, and we're going to from that derive the complex version of the Fourier series. Now just to note that I haven't put the subscript omega naught here in each of these, and I'll leave out that subscript omega naught in the rest of the derivation. It just makes it simpler for me to write it out, but it just be understood that when I write omega here, we are actually referring to omega naught, which is the fundamental frequency. And once we went through the derivations, I'll just add the omega naught back in at the end. So we have g of t equals a0 plus the sum from n equals 1 to infinity of an, and we replace the cos n omega t with this term here. And we've got bn, and the sine n omega t gets replaced with this term here. Now we just multiply out those terms and we get these four terms here. So there's 1, 2, 3, 4 terms. 1, 2, 3, 4 terms. We then note that 1 upon I is the same as minus I, so the first two terms remain the same, but the second two terms change. This I goes over up to the top, becomes minus I, so you get minus IBN upon 2, and this one becomes plus IBN upon 2. We then gather like terms in e to the I n omega t and e to the minus I n omega t, and we get these two like terms here. Now we also note that the sum from 1 to infinity of a function a to the minus n is the same as a sum from minus infinity to minus 1 of a function a to the power of n. So we use this little identity, and the first term remains the same, but the second term then changes. So instead of e to the minus I n omega t becomes e to the plus I n omega t, and the limits change from 1 to infinity to minus infinity to minus 1. We then note that we can represent this term here and this term here by a single term called Cn. So we have g of t equals the sum from n equals minus infinity to infinity of Cn e to the I n omega t, where the Cn plus, whenever n is a positive value, is equal to a minus IBN upon 2, and Cn minus, that is when n is a minus value, is a plus IBN upon 2, and the C0 equals a0. So we just finish up with a little taster of something that's to come later on in the video series. we've seen that we can represent the cosine function as e to the I omega t plus e to the minus I omega t upon 2, and the sine by e to the I omega t minus e to the minus I omega t upon 2i. And we drew this out before in the graphical calculator. We've seen it separately in terms of the cosine and the sine. Now I've drawn both of them here together. Now this is going to look a little bit busy, so you see this moving about. You can see it there. Okay, so it does look a little bit busy, but we'll go and we'll have a wee look and we'll try and understand where each of the terms are. So this term here, this line here, that's going to be our e to the I omega t, and it's travelling in an anti-clockwise direction. That's e to the minus I omega t travelling in the clockwise direction. Whenever we add them up vectorially, we get this point here. Now that point there will travel along this axis here, which is the x-axis, which is given by our cos omega t. So if you follow this little point here, you see it going from minus 2 to plus 2, plus 2 to minus 2. So we've seen that before whenever we looked at this complex function, complex exponential. Now I've got the same drawn here for the sine on the same graph. So again, we're dealing with this here, which is our e to the I omega t, which is in the anti-clockwise direction, and this one here is e to the, it's minus e to the minus I omega t, which is going to be travelling in the clockwise direction. And if you follow this point here, this is the vector summation of this line and this line. It travels up and down the y-axis, which is going to give us our sine function, but it goes from minus 2, so just keep your eye on the red dot. It goes from a plus 2 to minus 2 to plus 2 to minus 2. So that generates our sine function. Now we've seen from our derivations that we've covered, if I can maybe squeeze it in here. We've seen from this derivation here that we've got those 4 rotating phasors, so that's 1, 2, 3 and 4. And whenever we mess about with this and get it from this line to that line to that line there, all we're doing is we're just adding different terms together. And we can see that because this here is purely symmetrical, and whenever this one moves, that one moves at the same angle, and the same with this one and that one, it means in order to work out the cosine function, you could, if you wanted to, you could add half of the cosine of this one plus half of the cosine of that one to get the cosine. To get the sine, you can add half of the sine of this one plus half of the sine of this one to get the full sine, or equivalent, you could add half of the cosine of that plus half of the sine of that to half of the cosine of this to half of the sine of that to get the value for your cosine and your sine. So you can do it different ways, and that's all we're really doing whenever we're messing about with this equation here. Okay, and the one thing here to note is that there's a cute little, I suppose, mathematical trick here, is whenever we cover this line here, so we don't want to be dealing with e to the minus I n omega t and plus I n omega t. We only want one value, so the one value we get is e to the I n omega t. But the negative, or the phasors that rotate in a clockwise direction, they're going to be given by the value now of n. So n, in effect, previously was only an integer number, so like 1, 2, 3, 4, 5, but now n can range between negative values as well. So the negative value for the n represents or introduces the phasors rotating in the opposite direction. So it's a neat little mathematical trick there. Now I'll not go over it in any more detail because it can just get a bit confusing. You can maybe open it up yourself, have a wee look at it, and from what I've drawn, you talked about, you can pick out the different phasors. So there's one phasor here, there's two phasors, and there's that one again, which is 3, and this one here, which is 4. Now, we're only ever dealing with real functions of time. We don't have this, or we don't deal with imaginary functions of time. So whenever we transform a real even function in the frequency domain, we get a real even function. And if we transform a real odd function from time to frequency, in the frequency domain we get a imaginary odd function. So real functions, when we Fourier transform them in the frequency domain, they turn out to be functions of that particular type, and these functions are called Hermitian. And we will be dealing with the idea of Hermitian operators and the idea of eigenvalues and eigenvectors later on in the course, and that's just something to note and to look forward to there. And also, when we get into that kind of detail, you realise that the mathematics that we use and we're learning here can be applied as well, and they're applied in quantum mechanics. So that's quite a useful thing, and it's a useful aside for this course. And if you were to go through the rest of the course, it'd probably be quite useful if you were going to go and do some introduction to quantum mechanics. So let's go ahead and we'll simplify this even further. So the Cn plus is just the An minus Ibn upon 2. So the An can be written in this form here. So that's just our value for An that we worked out via the Fourier series. And the Ibn is just this term here, and we're dividing it by 2. So when we divide it by 2, we get our 1 upon t naught, the integral from 0 to t naught of f of t e to the minus I n omega t. This cos n omega t and minus I sin n omega t is given by that e to the I minus I n omega t. Now we do the same with the Cn minus. So the Cn minus is going to be given by the cos of minus n omega t plus I the sine of minus n omega t. Now the cos of minus n omega t is the same as cos n omega t, and the sine of minus n omega t is the same as minus the sine of n omega t. So it means that this thing here, Cn minus, is going to be given by 1 upon t naught, the integral from 0 to t naught of f of t, and this thing here again ends up as e to the minus I n omega t by dt. So we can say that the Cn minus is equal to the Cn plus. So now we'll rewrite this out, and we've got the f, we'll replace the g of t now with the f of t, because that's the function we started with. So f of t is the sum from now minus infinity to plus infinity of our value Cn e to the in, and we'll replace the omega now with the omega naught, because we know that's a fundamental frequency. So it's Cn e to the in omega naught t. And we know how to find the values of Cn now. The Cn is 1 upon t naught, the integral from 0 to t naught of f of t e to the minus in omega naught t by dt. So this here is our complex version of the Fourier series. So remember what we have here. We're approximating a function f of t using a series of other functions. Now these other functions here now are the complex exponentials. So the complex exponentials here, e to the in omega naught t, form an orthonormal basis, and this here is a constant. Now in order to find the constant, we have to form a dot product, and this here is the dot product. 1 upon t naught, the integral from 0 to t naught of the function times e to the minus in omega naught t by dt. So we're doing the same here as we've done with the Fourier series, and you can note that the value of 1 upon t naught now comes in because we need to normalise the vector space. So that's all there is for this video. We'll go ahead and we'll look at an example of using the complex version of the Fourier series. Thank you and goodbye.